little bit low, sir.
My voice, you can't hear me?
Yeah, I can't hear you, but
No, it's okay.
hello.
Yeah, is it okay now?
Yes, sir. Yes, sir.
Good, good. So, yeah, which topic are we discussing now? Are you going through now in the
Yes,
course?
yes, sir. Yes, sir. Sir, of course, I'm going through the course.
Yeah,
Last
which
time we
topic is this?
discussed the resonance excitations, inverse, Rutherford scattering, mood scattering. We discussed last time.
Okay.
And as far as assignments are concerned, we are solving the Cork model-based assignments.
Cork.
Yes.
So, do you have any specific concern, question?
Yes, sir. I would basically, I'm from electronics side. I am basically from neural dynamics, neuronal dynamics.
Okay.
Yeah. So, but my interest lies with, from my BSc my interest lies with core physics.
Okay.
Though I am this time employee right now, but still I pursue courses from NPTEL. This time I chose the particle physics.
Okay.
Basically, I want to know so that how can we solve quickly the problems regarding the allowedness and this non-allowedness of decay of particles. Basically, most of the particles I don't found on book, though I have bought book, but that's not that too much Griffith type book. But I want to know, sir, how can we solve? How can we remember? Because we have to remember the baryon number, lepton number for each and everything. But unfortunately, I'm not able to get some baryon number, lepton number of certain elements from the book. Yes, sir.
Okay.
Or do we have to just remember the that your goods have discussed the baryon octet and decouplets?
Yeah, I think yeah. For example, I can share some things and then just mention some this one. Is that okay? Based on this, and then we can discuss further. Huh?
Yes, sir.
So, for example, if we take a particular this, can you see the screen?
Yes, sir. Yes, sir.
So let's take this reaction. This is basically the beta decay thing. Okay. So, for example, if you take it to be n going to p plus e minus, what's wrong with that?
That's okay.
In terms of conservation numbers. Okay.
Yes, sir. Basically, electron is positive, neutral. Electrical charge will be conserved. Basically, proton will have positive one and electron will have negative one. Neutron will have 0. That will become 0, 0.
Yes, but there is something called lepton number also. Therefore, this first one is not allowed, whereas the second one is allowed.
Allowed, yes.
So the lepton numbers are like this. That is. Can you see this thing now? So we have three different types of this. Unfortunately, we have to kind of remember, but there are not too many particles.
Sir?
Yeah.
Happy Teachers Day, sir.
Yeah. Thank you, Abhinav. Thank you. So this only a very few list 2-3 particles are there. Three electrons type of particle, charged particle, and 3 neutral particles called neutrinos. So it is easy to remember here. For electron, you have a particular type of charge or quantum number called lepton number corresponding to electron. We can call it Le, and that's 0 for protons, neutrons, and all those particles. So if you consider this first one here, first reaction here, the electron has a number, for lepton number 1, and that should be 0 total together. There has to be therefore another particle which has a lepton number -1. And as you said, electric charge is also already conserved. So that new particle has to be a neutral particle, electrically neutral. So neutrino or anti-neutrino fits well. So anti-neutrino is the one that we can have here. So considering the conservation rules, this is the way that would go. Okay. So this is okay, E minus nu E, that is not allowed. The first one, this one, okay. The first one here is not allowed because electron and neutrino, you can see from the table that electron and neutrino both have lepton number 1, 1. Okay. Therefore, that is not allowed. Okay.
Yes, sir.
And second one, what is the problem? Second one, the problem is that it is electron and muon type neutrino. Then also it is different charges, so that is not allowed. And similarly here, for the tau going to mu minus, you have to have something else also with that. Whereas tau going to mu minus plus nu this, that has a problem also. What's the problem with that? The problem is that the tau is also a lepton. So initially you have a tau lepton. So that has, there is already a lepton number of tau type, L tau, which is 1. So the right hand side should also have a L tau 1. That's why only the last one below that allowed this one, last equation. So if you look at the last equation or the reaction here, so tau lepton number is 1 initially. Then on the right hand side, there is a muon and an anti-muon. So their lepton number and our lepton numbers are cancelled. And there is a nu tau. Nu tau has a lepton number 1. So it matches. So this is what you have to do. So what you have to do is to actually kind of remember this, but remembering this is not too hard in the sense that there are, it's like electron and electron type neutrino. There are only 2 of them. They have Le equal to 1. All other quantum numbers are 0, or lepton numbers and baryon number, etc. are 0 for that. For muon and muon neutrino, it is L mu which is equal to 1. So L mu and Le has to be separately conserved. Okay, so that is one thing which you have to keep in mind. Is it slightly better? I can try to actually I send this slide, or you can take a snapshot or whatever, and I can see if I can make a complete list of this and then send it. Okay.
That would be great, sir.
Okay, that I will do.
Yeah, thank you, sir. And sir, one more question which I encountered last time while solving the assignment is that how can we identify whether it is a weak kind of reaction, whether it's an electromagnetic? Though electromagnetic, we can say that photon is going in the reaction that that is electromagnetic. But in general, how can we identify which type of reaction is this?
Yeah, so that is a little harder, and in just looking at the process like this. Okay, one way, one immediate thing and thing is, if you have a neutrino, for example, okay, neutrinos, then that basically is a weak reaction. You cannot have, neutrinos have only weak interactions. Okay, neutrinos take part only in weak interaction, and usually for electromagnetic interaction, you have a photon with it. Okay, but that's not entirely so, because if you have a scattering like electron positron going to electron positron, you don't really have photon in the initial or final state, but that can still be electromagnetic also. Okay, so but for most of these reactions, one thing which is sure is that if there is a neutrino involved in that, it is definitely a weak interaction. Okay, so other things are slightly more involved. What we are going to do in the rest of the course, when we are actually going to discuss from lecture number in week 9, I think. Is it week 9? Yeah, I think it is week 8 and week 9. Week 9 we can. So this is 8th week which is running now, or 9th one already.
Coming will be the 8th. Coming lectures will be the 8th.
8th week. So one more week after that, so this week, in week 8, we are going to discuss some of these relativistic kinematics and things like that, and electromagnetic interactions. And then when it is coming to the weak interactions, okay, we are going to actually discuss that in a little more detail. Okay, so maybe it will get clearer there. And then in the next live session, or you can send me discuss it in the forum, or send me this thing at that time. Maybe it will become a little clearer, little more clear. Okay.
Yeah, about the electromagnetic reaction, that is clear, Manu, that it has to electron, positron, or a photon has to be there.
Yeah. So, but then if weak interactions are mediated by something similar to this photon, but what's called W boson, etc. Okay.
Yes.
But
Yes, sir.
generically speaking, there will be, if there is a neutrino, then that is for sure that it is a weak interaction, because neutrinos do not have any other interactions.
What does sir muon denotes?
Muon is like electron. Like electron, it has a negative charge, 1 unit, and it is light, but lighter than proton, but it is heavier than electron. So it is similar to that electron in most of the properties. So that's a muon. So muons are found in cosmic rays. Actually, that is where we discovered them first.
That will indicate that it can take part in the electromagnetic interactions.
Yes, it is. It is similar to electron. It can take part in electromagnetic interaction as well as weak interaction. Weak interaction. So leptons, like electron, muon, neutrinos, they cannot take part in the strong interaction. They will not be part of the strong interaction. So if they are there, that is not a strong interaction. That is for sure. But it could be either electromagnetic or weak interaction. In fact, in many cases, electron and muon, many of the reactions will be mixed. Mixed in the sense that it will have contribution from both electromagnetic and weak interactions. But if there is only neutrino, then it will be simply weak interaction, no electromagnetic interaction. So muons and tau leptons, charged leptons, electrically charged ones, they can take part in both weak interaction and electromagnetic interaction.
Thank you, sir.
Yeah.
Thanks.
Okay. Abhiram, you have some questions, or you are okay with the course?
No questions, sir, now.
All right. Good. Yeah. So as I said, from next week, we are going to actually start the electroweak interactions, and then so it will be slightly more involved. In fact, we have to also look at the relativistic formalism. There will be relativistic electrodynamics, a Dirac equation, and things like that would also be discussed. So it's going to be a little more involved in terms of this one. So if there are any questions at any stage, anything that you have difficulties, you can send a message in the forum, and then we will address that thing. Okay. Or in case you want me to personally look at it, you can send me a mail as well. Okay.
Thank you, sir.
So Shubhi, are you okay with the course? Everything is okay? You have any specific question?
Thank you, sir. Till now it is going good.
Okay.
Assignments are also going good, and theory is also going good. Till now it is okay.
Okay. Very good.
Hello, sir.
Yeah.
I have a question about electron. Is electron is an elementary particle?
Yeah. Yes.
Like because we can't say that proton and neutron is elementary particle. So
Right.
I want to know about electron is elementary, but what is I think lepton numbers is denote how what's form how forms lepton? What is lepton? Uh, what is lepton number? Like I know about quark model, quark
Yeah.
inside the proton neutron, but is lepton inside? I don't know. I think lepton is not inside the element. Sorry, lepton is not inside the electron because electron is elementary particle. But where is lepton? What is lepton? And how it feels? How I can say this is lepton? This is lepton reaction like.
Okay. Yeah, it's like this, that it is basically lepton is a category. It is not a particle. It is a category of particle. Like we have different quarks, electron, muon, tau. These particles, along with 3 neutrinos, these 6 particles are called leptons. So it is just a name for that group of particles. Okay.
Oh.
So it is like saying that proton is a baryon, neutron is a baryon. So they come in the category of a group of particles called baryons. And quarks, there is up-type quark. There are 6 different flavors, a different type of quarks, and they are, so quark means it's not a particle, it's a category of particle. Similarly, lepton is a category of particle. So, and as you said, electron is an elementary particle. As far as the standard model is concerned, it is a structureless point-like particle. So it does not have any further structures. Like there is nothing that make the proton. It is a small particle which cannot be divided. But people are still experimentally, people have been trying to actually probe this, whether the electron has substructures, whether there is any structure to that. Like I think we already discussed the deep inelastic, or maybe some of this are going to be discussed now this week. Deep inelastic scattering, which probed the proton and then experimentally showed us that proton has structures inside that. So it is basically the experiment which tells us that, okay, it looks like it is made of some smaller bump. It is like the Rutherford scattering. You are familiar with Rutherford scattering. Rutherford scattering very clearly said that atom, like if you look at the Dalton model of atom, Dalton's model or the earlier model, which actually said that it is some which is a small unit which cannot be divided further. But it is, everything is made of this. All elements are made of such small units called atoms. But then Thomson experiment actually said that that there are electrons. We had cathode ray experiments. Cathode rays were emitted from atoms. So therefore, we know that there are negatively charged particles coming from the neutral atom. So that was the one point where actually we realized that experimentally, certainly, that there are structures to the atoms. And then further on, Rutherford said that, okay, there is this nucleus, which is basically at the center of the atom. So that is also coming out from the experiment, the scattering experiments. Like that was with alpha particle. Then further now, later on, we did experiments with electrons on proton. Instead of the gold foil, you take gas, hydrogen gas with some high density. That is proton basically. And then send high energy electrons instead of the alpha particles. And that probed the proton, because the scattering of these electrons of the proton would give information very similar to Rutherford thing, but it is slightly more involved. So that is what is called the deep inelastic scattering, which we have included in the course, which is basically telling us that we have proton is not an elementary particle, but it has structures. Similarly, all these experiments, like what is going on now, the state of the art high energy experiments, are trying to ask this question: are there any signatures similar to those or different from that, which actually tell us or indicate any structure within the electron? So far as we have not really seen any of these structures or any indication of such structure for electron experimentally. And theoretically also, we can actually do everything consistently by considering electron as a point particle kind of a thing, an elementary particle. Okay. So, but this question we keep asking still further, and then there are dedicated experimental groups which are probing the question, actually asking this question and trying to find answer to that.
Okay, sir.
Similarly, quarks are also elementary so far as standard model is concerned. So we can say
Yes.
that we can say that the quarks and leptons. When we say leptons, it's the group of particles which involve electron, tau, neutrino, muon, neutrino, and then electron, muon, and tau, all the charged particles, and the neutrinos. And they and the quarks. Again, quark meaning we have these 6 different type of quarks. They are all elementary.
Yes, sir. Because yes.
Okay.
Quark makes a proton or neutron, and their charges.
Your voice broke actually. Can you repeat that again?
Sir?
No, I think some disturbance is there.
Actually, okay, sir. Now I understand.
Okay.
What is the electron and quark?
Okay, good. So, yeah.
Yes, yes, sir. There is a slow network, bad
Okay.
network.
You can actually put it in the chat also. Okay. I can, if there is a question, then you can put it in the chat, meaning chat of this meeting. If, okay. All right. So others, are there any further questions? Good. I am happy that you are all enjoying the course. And now, from now onwards, it is going to take you slightly more into the actual elementary particles. So we have kind of discussed the nucleus, then the various dynamics related to the nucleus, and then we have looked at the nucleons, which is proton, neutron, and particles similar to that, their dynamics, their classifications in terms of the quark model and things like that. That is how things evolved in the 20th century. In fact, it is amazing that so much happened in the 1 century, in the 20th century itself. And then going further, it actually we developed this model for the dynamics of the quarks and leptons, like which make the quarks which make all the baryons like protons and neutrons, and all the other elementary particles called leptons. So quarks come in a category, leptons come in another category, but they have a lot of things. They both have electromagnetic charge and they both have weak interactions also. But leptons do not take part in strong interaction, whereas quarks take part in all the 3 interactions. Gravity, anything which has mass or energy will take part in gravitation interaction. So, but we are not considering that in our course because it is too weak, too insignificant. Not because it is not there, but it is too insignificant at these scales, at this for the elementary particles. Gravity becomes very, very important in the large scale, and then when there are a lot of matter, when there is a lot of matter there, like in the cosmic astrophysical situations where we have very heavy and large masses, and there it is basically the gravitational interaction which is important. Whereas in this case, wherever we are talking about subnuclear small particles but high energy or very high energy in the sense that in terms of the atomic energies, but these gravitational interactions are not important. So, but therefore, we won't talk about it. But otherwise, quarks take part in all the three interactions: strong interaction, weak interaction, and electromagnetic interaction. They are electrically charged. They also have the corresponding charge or whatever is needed, whatever the quantum number needed for strong interaction and weak interactions. Whereas leptons, charged leptons are there, neutral leptons are there. Charged leptons are like electron, muon, and tau lepton, and all the three of them, they take part in charge electromagnetic interaction as well as weak interaction, whereas neutrinos take part only in weak interaction. They do not have the strong charge, they do not have the electromagnetic charge, but they have the weak isospin or the weak charge. Okay, and now we are going to actually discuss further these dynamics in more detail in terms of the gauge interactions and things like that. So we will come to how we consider the photon, electromagnetic field as the photon, the quantized form, the photons, and then how that interaction in terms of the photon or in the quantum electrodynamics, how do we see that? For example, the electron scattering on electron or something like that. In fact, photon as a particle was recognized. There are very, I mean, electromagnetic interaction or the quantization of all these things can be is needed to understand photoelectric effect. That is something which in 1905 Einstein told us. So that's one of the places where the particle nature of electromagnetic interaction comes in, or that is where the photons property as a particle is visible. But there are also other experiments, like there is something called the Compton scattering. Compton scattering is light scattering on electron. So that kind of a reaction is possible, or the properties of that reaction when we study that, that is, it is clear that we need the particle property or the photon as a quantized form of this electromagnetic interaction is needed. So some of these things we will actually do in the next couple of weeks, and the scattering cross-section calculation and then some of these ideas would be discussed and for the elementary particles. And then I think we also mentioned what is the standard model towards the end, and whatever is missing or whatever we couldn't do in the course itself, I think in the next discussion, I will try to see if I can actually present, because now it is a little bit premature to do that. So maybe by the time we have the next live session, we can actually have, I can kind of tell a little more about the standard model or some such things. There are, yeah, a lot of interesting things there. And then let me know in advance if there are some topic apart from specific questions. Suppose you want to know about certain specific things, okay, topic which is related to what we are doing, but which is not really covered in this one. And then if you tell me well in advance, I'll be able to talk about that a little bit, at least in the next live session. Okay.
Okay. Okay, sir.
Yeah.
Sir, actually, sir, I want to know about muon G2 experiment. Last live session, I will request.
Yeah.
Muon
G
G2.
Yeah.
Sorry, mu on GO2, mu on GO2 physics.
Yeah, there is G minus 2. I mean, like there is an anomaly with this thing. Okay.
Experiment by Fermi lab.
Yeah. So maybe I told you maybe in this live session we may be able to do that, but I think you'll have to wait a little more, because the next session we will be able to discuss that, because there are some little bit more of the dynamics that we need to know about it. Okay. It is basically happening because of the quantum corrections, as I told you that time.
Right.
Yeah. So, but discussing that quantum correction itself and then talking about what's happening in the standard model need a little more information. I was not sure when this live session would be. I was actually thinking that it would be a little later than this, but somehow this was the period that was available for us. So course did not really progress up to that, but you need to go up to, I think, 10th week or 11th week or something like that, and then we would be able to really discuss these things. Okay. I think Abhiram something is wrong with his network. Others? Yeah. Any further questions?
Yes, sir. I have clear. It's not a question. It is about the clarification.
Yeah, please.
Yeah, basically, sometimes we write pi minus or some particle decays to some products. Let's suppose, can we write them in product? For example, there was a question that was pi minus decays to mu minus, e minus, and e plus. Without addition operator. Can we write like them in product?
Oh, that's just a way of representing it. It is okay. I mean, as a convention, it's for example, here, I have written it as P plus E minus plus nu. That is a convention. We can write it without that plus also. Many people, I mean, many times I myself actually don't use that. I was a bit, I mean, I use both. So you can use either, no problem, as long as it is distinguishable.
Oh, thank you, sir. It was about the clarification.
All right, that you can do.
Thank you.
Okay. Any other questions or comments or assignments? Do you think it is okay? So if there is any specific general pattern comment that you have.
No, sir. Assignments still week 6 are good.
All right, very good.
They're good.
Where are you from?
I am from Jammu and Kashmir.
You are from Jammu and Kashmir. Which institute? Yes. Oh, you are working there, you said.
Yeah, I am. I'm already. I'm a government employee right now.
Okay. Good.
But I like to know about my first love. That's physics.
That's very good. Yeah.
Though I pursued my master's in electronics, but now I have pursued already classical mechanics and electrodynamics, and I have pursued some courses in electronics. Now I am pursuing particle, and hopefully in winters I will go for quantum mechanics.
Okay, that's very good. That's very good.
Yeah. Basically, I have done my doctorate in electronics.
Electronics, I see. Okay,
it's
good.
On fractional order networks. Fractional order networks in neurons, artificial neurons.
All right, good.
Basically, I have pursued my BSc in physics. That is why my interest is still lies with physics.
Good. Okay, that's very good. So if others don't have any questions also, then maybe we can close the session as well. Mukesh, Bharati, Noor, Subi, these are the people I can see here. All right. Okay, so see you all then. Let's continue the discussion, not just along in the live sessions alone, but also in the forum and other ways through email or whatever. All right. So all the best to all of you for the rest of the course and all other courses that you are doing now, and also in the future career that you have ahead. Okay. All the best then. Bye bye.
Thank you, sir. Bye.
Thank you, sir.